Welcome. Welcome to Module 4 of Part 1, which deals with refrigeration cycles. In this module, we'll cover implementation of the cycle in detail, especially vapor compression cycle. We'll solve a problem manually and verify using test code. And the prereq for this module is Part 0 of the same module, where we discuss the basic refrigeration cycle in terms of a closed steady system. And in module 3, we covered the PC model, so you make sure that you are familiar with that. And in module 2, part 0, we discussed open steady devices. So we'll draw upon all the knowledge from these different sections in this particular module. Okay, so let's get started with an implementation of the vapor compression cycle. Well, a cycle means you can start anywhere and go around and come to the same point. So let's start at point 4. Let's say we have a very, very cold saturated mixture of liquid and vapor, state 4. Very, very cold. And our cold region is TC. Let's say we want to maintain it at 0 degrees Celsius. So suppose at state 4, the liquid vapor mixture is really cold. Let's say it's -5 degrees Celsius. It's a liquid vapor mixture. As it enters what is called an evaporator, which is another name for a boiler really, it finds a very hot surroundings around it. Notice that this fluid is at -5 degrees Celsius and the region around it is at 0 degrees Celsius. So obviously heat is going to flow from the cold region to here, and that's our q.c, the cooling load we discussed before. So as heat enters the evaporator, the liquid inside evaporates or boils, and as the phase change occurs, we follow a constant pressure line. As heat is added, the pressure doesn't change in the evaporator, just like in a boiler in case of a steam turbine cycle. So from 4, the state keeps moving to the right without changing its temperature until we reach state 1, where we have, this is the G state, which means it's a saturated vapor at state 1. So what happened is that we picked up a lot of heat from state 4 to 1, which is proportional to the area underneath. So q.c is proportional to this area. And as we can see, in the evaporator, the temperature doesn't change. It always remains at -5 degrees Celsius, whereas the fluid changes its phase. And because the atmosphere, the surrounding cold space is a temperature 0 degrees Celsius, the differential of this temperature drives the heat transfer. So this is the heart of the refrigeration cycle, the evaporator, where essentially a very, very cold liquid boils off as heat is added. So at state 1, we have a saturated vapor. That's for an ideal vapor compression cycle. And then we compress it isentropically. Again, you're familiar with isentropic compression. The entropy remains constant. It's an ideal compressor. How does the compressor operate? It doesn't matter. As long as it's adiabatic and frictionless, it will be isentropic. From state 1 to 2, therefore, we compress the vapor. So when you compress a vapor, it is similar to compressing a gas, so the temperature also rises, pressure also rises. So at state 2, we have quite a high temperature. Let's say the temperature is 50 degrees Celsius, or let's say the temperature is 60 degrees Celsius at state 2. Now, at state 2, we have superheated vapor at a higher pressure, and at state 2, we send it to a condenser. What happened in the condenser? Just like a vapor power plant condenser, the vapor going through the condenser cools down. Heat has to be rejected. And suppose the outside temperature is, let's say outside temperature is 20 degrees Celsius. Then we have to make sure that as the vapor condenses, its temperature is never, it can never be below 20 degrees Celsius. So suppose this temperature is 25 degrees Celsius. So if the temperature at state 3 is 25 degrees Celsius, that means from 60 degree, the temperature will come down to 25 and temperature will never change. And the difference in temperature, 25 minus 20, will drive the heat transfer. So that's where our Q dot H will take place. So at state 3, we have saturated liquid at a temperature slightly higher than the atmospheric temperature. Again, we're taking TH to be 20 degrees Celsius and TC to be 0 degrees Celsius in our example here. So at state 3, the liquid at the end of the condenser, instead of using it in a turbine, what we use what is known as an expansion valve. In an expansion valve, what happens? The pressure drops rapidly, and because there is no heat transfer, you can show that if there is plenty of friction, it is possible to reduce the pressure. So it's not an isentropic expansion. It's quite the contrary. The pressure drops because of friction. We can show that enthalpy remains constant and the temperature drops. Again, we'll analyze the expansion valve in details again. We have done it in chapter 4 in your previous thermodynamics class. But again, we'll analyze this and show that enthalpy remains constant. So in summary, at state 4, we have a mixture of saturated liquid and vapor, and it boils in the evaporator, comes out as a saturated vapor at G state, which is compressed isentropically to state 2 to superheated vapor. From there, it's cooled at a constant pressure where the heat out or Q dot H happens. This is where Q dot C happens. So at the end of the condenser, the fluid after it condenses comes out as a saturated liquid at state 3, and there it expands in the expansion valve where enthalpy remains constant, we will find. And as a result, the constant enthalpy line in a TS diagram looks somewhat like this. Entropy is increasing while temperature drops, and we complete the cycle. Okay, let's go device by device, and then the picture will be clearer. Okay, so we start with our compressor, isentropic compressor. We understand the energy equation will be immediately clear. dE dt equals m dot H1, that's the enthalpy energy carried by the flow. M dot H2 is the energy that is coming out, plus Q dot, which is 0, minus W dot external. Steady state. So 0 equals m dot H1 minus H2 minus what is W dot external? W dot external is really W dot compressor, but W dot C is a positive number, so we must put the sign negative here. Again, this is following the Win-Hip sign convention, as you understand. Work in is negative, so W dot C is a positive number. When you say compressor power, 5 kilowatt, that means 5 kilowatt is going in. You don't need another sign to describe it. But W dot external here has a sign attached to it. It's an algebraic quantity. So we have to be respectful to the sign. And when we substitute W dot C, which is a positive number, we put the negative sign to reflect W dot external. In other words, W dot external equals minus W dot C. So therefore, the equation simplifies to W dot C equals m dot H2 minus H1, which is kind of obvious. The work going into the compressor equals the energy coming out minus energy going in. And if we use the entropy equation, it will be clear that entropy doesn't change in an isentropic, in an ideal compressor. Okay, so let's show that just for the sake of completeness. M dot S1 minus M dot S2. These are the different ways entropy can change as it goes through the compressor. Steady state, there is no net rate of change of entropy inside the compressor. No heat transfer, and an ideal compressor, no friction. And that tells us S1 equals S2. So in a TS diagram, we always, in an ideal system, state 1 will be always saturated, and we'll go isentropically as the pressure increases. So this will be the plot of the compressor in a TH diagram. Okay, let's move to the condenser. Again, let's quickly use the energy equation. In a condenser, heat is coming out, Q dot out or Q dot H, whatever you want to call it. So energy that goes in, energy that comes out, Q dot H will be the difference between that, and you can practically write it without going into the energy equation. What is Q dot H? The energy that goes in is higher than the energy that comes out with the flow. So the difference must be heat that is coming out, Q dot H or Q dot out, whatever way you want to describe it. And another thing, whenever there's a heat transfer in a flow, always resist from immediately assuming that heat transfer will affect the pressure. It doesn't. Heat transfer only affects the pressure of a fluid when it's in a closed chamber. And when the fluid is free to move, it doesn't affect the pressure at all. So because of friction, actually pressure may drop slightly, but we'll neglect that in an ideal condenser. So in a condenser, essentially it's opposite of boiling. So if I have state 2 here, pressure remains constant, this constant pressure line, and at the exit of the condenser, it's always assumed that I have a saturated fluid. In other words, this is my F state. Okay, let's move on to the expansion valve. Okay, so let's go over the energy equation very quickly. The EDT, again, m dot H3, m dot H4 plus Q dot minus W dot external, right? If we neglect, well, for steady state, the EDT equals 0, and if there is no heat transfer, of course, there is no external work transfer here, no shaft, electricity, etc. So therefore, as you can see, H3 equals H4. So expansion valve is called isenthalpic. Well, but as you can see, if we use the entropy equation, you can immediately see entropy will increase because the way the valve works is through friction. And we know friction can be greater than, whenever there's a friction and S dot J is greater than going to be 0, this is the second law of thermodynamics. It can be equal 0 for a reversible system. So steady state, no heat transfer, and immediately it's clear that S4 equals S3 plus a quantity that can never be negative. So therefore, this must be greater than S3. S4 equals S3 in an isentropic process like in a turbine or compressor, but friction is essential in this case. This is also known as throttling. In what happens is called throttling. The flow is throttled. So in a throttling device, like an expansion valve, what happens is that entropy increases. So in the TH diagram, let me make a small diagram here. State 3 was the condenser exit state, saturated fluid, and pressure must drop. So we must be on this low pressure line, and entropy increases. So what happens is that we move to the right, and that's why it looks like this. Finally, let's analyze the evaporator. In an evaporator, the EDT equal m dot H1, that's what energy coming in, m dot H4 plus Q dot minus W dot external, simplifies as no external work. 0 equals m dot H1 minus H4 plus Q dot. And Q dot is what? Heat is that is added right now. So Q dot and Q dot H are just equal, right? Because both are positive. Q dot H is a positive number, and Q dot we know is when heat is added, the Win-Hip sign convention will tell us heat in positive, work in negative. So therefore, Q dot equals Q dot H, we get an expression for heat added, M dot H4 minus H1, which is kind of intuitive. So that completes all our energy transfer equations, and we can easily find what is W dot net. Of course, W dot net is nothing but W dot C. We have no work coming out of a turbine or anything, so this is the work required. And Q dot in equals Q dot H, so therefore COP can be found out from the desired quantity, which is Q dot C and Q dot Okay, let's go and analyze the evaporator now. What happens in an evaporator is that heat is added, Q dot C, that's our cooling load. And the energy that comes in, energy that's carried out by mass, oops, the wrong way, energy comes in here at state 4 and goes out at state 1. So if we do an energy analysis of the evaporator, M dot H4 is coming in, M dot H1 is going out, plus Q dot minus W dot, that's the standard energy equation, steady state, no external work. And we recognize that Q dot and Q dot C are equal through our Win-Hip convention because heat in is positive, Q dot C is going in. So we can substitute that here, 0 equal M dot H4 minus H1 plus Q dot C, or Q dot C equal M dot H1 minus H4. Obviously H1 will be higher than H4. So that's how we got our cooling load. And finally, W dot net in a refrigeration system, vapor compression cycle, is W dot C because there is no other work transfer, and that's what is going into the refrigeration system. So COP can be now obtained from Q dot C divided by W dot net. So now we have developed formulas for energy transfer on each of the devices. One thing I didn't mention that I routinely assume J and H are equal. Recall that J equal H plus KE plus PE, and we neglected the contribution of KE and PE in the entire analysis.